Hey everyone, welcome back to another Calculus 2 video. Today we're going to talk about area, but area in a different sense. Area between two curves on some region on the x-axis A to B. There's my area there, and by the way, I'm going to be using area in this video in the standard geometric sense. It's not the weird Riemann sense where we can have negative areas and positive areas. I want to ask this question in the plain geometric sense. What is that standard area in blue? Well, I'm going to form that area in blue by a little part-hole analysis here. That pink area, pink region, the right Riemann sum is given like so. And then that bottom region is given by this green definite integral. Notice both these regions, the pink and the green, border the x-axis. Their lower boundary is concurrent, is collinear with the x-axis, and that allows us to write a definite integral expression. And then from there we subtract away the area we don't want to get the area we want, which is that area in blue. And there he is. There he is. Now, of course, the bounds of integration match, which I've underlined there in yellow. And given that, I can smush them all into one definite integral, and so I get a nifty expression for area between those two curves. And again, just to reemphasize, as long as f is bigger than or equal to g on my particular interval of interest, this area, this definite integral here, will always yield not just the weird Riemann area, but area in the standard geometric sense. The actual area bound between those two graphs. And this may not seem profound, but remember, definite integration does not immediately give us the area that we see on the page or the screen. It could be a negative number. It could be 0. So, I guess here, let's illustrate real quick. If I integrate like an odd function from negative 3 to positive 3, let's say x to the 5th, that's going to be a 0. Well, why? Because the Riemann area to the left of 0 is exactly the same magnitude as the Riemann area to the right, but one is positive, one is negative. They offset each other, and we get 0. But clearly, I mean, there's some pink space taken up, so it's not the area, not the actual geometric area. Same deal here. If I go from negative 4 to 0 of x, I'm getting a negative number, which doesn't gel well with our standard geometric definition of area. By the way, to get the actual area, we'd have to take the absolute value of our function and then integrate. So that's a side point. It might become relevant in a future video, but we're gonna ignore that for now. Here's another thing. If I swap my bounds of integration, if the lower bound is bigger than the upper bound, I'm gonna get a negative number. Should my graph be above the x-axis? But this is a special case. We don't have to worry about this too much for this video, because anytime we see an interval, an x interval AB, closed interval AB, it's just automatically presumed that A is going to be less than B when we're talking about domains or intervals on the x-axis. Now then, let's see this in application, and I'll do it in maximum intuitive detail for you before doing some future problems in quicker fashion. Find the area bound by the graph of this parabola boy, negative x squared plus 9, and let's say g is the flip of that, x squared minus 9. So x squared plus 9, negative x squared plus 9 anyway, is a downward facing parabola with a y-intercept at positive 9, and g is an upward facing parabola with a negative y-intercept. And find the x-intercept, of course, we set 1 equals 0. I'm going to start with f, set equals 0, solve for x. There we go, that's the region. That's one area I want to find. But I also want to find the other one G. But first, let's see what this area or this definite integral in purple is. As you should suspect, this is going to be a positive number. In this case, the Riemann area is the actual geometric standard area. Computing like so gives us positive 36. Positive 36, which I'll label on the picture. And now for the other parabola fella, of course we should expect in the Riemann sense he's going to be a negative number. And by symmetry, they have the same reflective symmetry. So this guy's going to be negative 36. So clearly by inspection, the actual area sandwiched between these two graphs is going to be positive 72, 36 plus the absolute value of negative 36. So does this comport with our formula that we've written down here? Well, let's tinker around with it and see. -3 to +3 of the upper bound, given by f, minus the lower bound, given by g, lets me simplify like so, and I can yank on out a +2, and I've regenerated my first integral in purple. There he is, and we do indeed get a +72. So at least the formula checks out in this case. The reason why, though, it's going to check out in every case. Suppose we have, say, this time let G be below the x-axis and F's above. If I form a rectangle there in red, there in pink in the standard Riemann sense, I form another Riemann rectangle for G. F of xi times delta x is going to be the Riemann area anyway of that pink one, and G of xi times delta x is going to be the Riemann area of that green one. And of course that first product's going to be a positive number, that second product in green's a negative, but notice, positive minus a negative is plus. Positives all around. And that's exactly what I'm doing when I do this formula. I'm getting the actual area of that thing in gold, that big rectangle in gold. That's why this always works. That's why this formula always going to work. Alright, another example. Let's switch it around just a bit. Find the area between, let's have another parabola, x squared minus 5x minus 7, and a nice linear fella, x minus 12. Find the area between those two graphs over the interval -2 to +5. Now we have to be careful because, I don't know about y'all, but off the top of my head, I don't know which one of these is always above the other one, or maybe if one is only sometimes above the other one on this interval. So we got to do some interval testing. We got to find where these two guys intersect, because those are the demarcations between when one goes from being above the other as opposed to being below the other. So first, let's find our points of intersection. I'm going to set them on equal. Solve, solve, solve. And here we are. They intersect at the points whose x-coordinates are 1 and 5. And 1's the only one I really have to worry about because 5 is the end point of my interval. Now I'm going to presume I don't know the picture. Because some problems you will have to do these without a picture in front of you. Or it's just going to be too hard to create a picture. So let's do it the hard way first. Let's see if we can divide up my interval of interest, -2 to +5, like so. And indeed I can. I divide it up like so, and I notice I did not include the POIs, the points of intersection. Now on these two sub-intervals that I have created, I want to figure out whether f is greater than g always, or g is greater than f on each one. So first I'll do it for -2 to +1, and then +1 to +5. Let's do that up here in purple. Let's do it up there in purple. I'm just going to pick a random number, nice convenient number from inside each one, and I'm going to throw them into f and g. If I throw 0 into f, what do I get? Well, I believe that's going to be a -7, and likewise throw 0 to g, I get a -12. On the other hand, if I throw x equals +2 into f, I get a -13, and I get a -10 for g. Now what this means is on that first interval, -2 to +1, f is always greater than g, whereas on that second interval, 1 to 5, g is always greater than f. By the way, I know this is true because if they were ever switched for either one, then I would have more than 2 points of intersection on the interval, which I've just discovered cannot be the case. Well, now we just apply our nifty formula to each of these intervals individually. The area, the actual standard geometric area between the graphs on -2, 1 is given by the interval of f minus g with those respective bounds, whereas the area between the graphs on 1, 5 is given by g minus f with those respective bounds of integration. One's always bigger than the other on each one. Therefore, I just combine the two, add them together, and this gives me my answer for the area. Do a little standard integration computation, And this is going to come out to be 113 over 3. I'll let you do that on your own. I'll let you fill in those details. But just as a note, and you could have done this for this problem, but I wanted you to see the difficult way of going about things in case you couldn't do this, but in this case you can do this. And what do I mean by this? Well, I mean sketching a graph. Having a nice picture in front of us to get our bearings straight. So what does this graph look like? Well, of course, F's a nice quadratic boy. And we know the x-coordinate of the vertex of any parabola is negative b over 2a. By the way, in case you're fuzzy on why that's the case, why the x-coordinate of a vertex of a parabola is negative b over 2a, well, let's start with our standard definition of a quadratic and the basic visual fact that at the vertex your slope is 0. Whether it's an upward parabola or downward at 0, set that derivative equal to 0, and solve for x. Subtract b to both sides, divide by 2a, negative b over 2a. And here he is. In this case, 5 over 2. We have a y-intercept at negative 7. Again, on this point, I'm just filling in some detail to get a reasonably decent graph. There's my negative 7. 5 halves around right there. Now the vertex is going to be below negative 7 because it's an upward facing parabola. And here he is. Next to g is going to be a line. And of course we graph him like so, negative 12. And I have my points of intersection at 1 and 5. 1 and 5. So by the way, before you graph, you should still try to find the POIs to get your graph maximally fleshed out in detail. Because then it's useful, then it's maximally useful. And now look, we can clearly see that on 1 to 5, the green graph is above the red graph. The green graph is what? It's G. On the other hand, from negative 2 to positive 1 for our x values, the red graph is always above the green graph. In other words, f is always greater than g on that particular interval. So no interval testing needed. We just fall back on our picture and see. We look and see which one is above the other on our particular subintervals of our overall interval of interest. So here's what we did. That first little region in yellow was the f minus g interval, and that second little bitty one is the g minus f1. And together they are both 113 over 3. And that's the way it is. It's the way it works. The actual standard geometric area, not any weird Riemann stuff. That is actually what it is, actually how much space it takes up. 113 over 3. Now, let's do another one. And for this one, this one's a bit of a party. There's going to be quite a bit going on, and a picture becomes practically necessary. We could do it with interval testing, but it would just be an analysis overdose. We've got 3 things, 8 over x squared, and then 2 lines, 8x and plain old x. Picture time, picture time. There we go. And I'm underlining them in the colors they represent. The steep line is the 8x, and the flatter line is the x, and of course the hyperbolish. It's not really a hyperbola, but you guys know from pre-cal foundations that is going to be 8 over x squared in purple. Now that area in yellow, I'm going to purposely divide it into 2 regions with a straight vertical line segment, because if I do that, then that white boundary that I've created corresponds to exactly 1 x coordinate, which allows me to do some integration stuff. We'll call that sub-area, in blue, area 1, and likewise the pink area, area 2, area 2. And I can get expressions for each of those sub-areas. Area 1 is going to be the definite integral of the green graph minus the red graph. The green graph's above the red graph on that particular interval. And likewise, the area in pink is going to be the purple graph minus the red graph on a particular with particular bounds of integration, but I don't know those yet. Why don't I know those? Well, I'll tell you, friends, I forgot to take the POIs. We need POIs to put numbers into our bounds of integration. So there are my 2 POIs. There's another one with the origin, but he's obvious. So I'm going to focus on those first 2. Set the purple graph equal to the green graph. 8 over x squared equals 8x when x is equal to 1. X is equal to 1. And now for the other POI, where the purple graph hits the red graph, 8 over x squared there, it'll be equal to just plain old x. Solve for x and multiply through by x cubed equals 8, and x is positive 2. There are my bounds of integration. See, now I've filled them in up there. Filled in the appropriate bounds of integration, and area in yellow is going to be area in blue plus area in pink. Simple part-whole analysis that you guys are accustomed to doing on standardized tests and from previous classes. We just do them individually, add the two definite integrals, and we get 6. That's how the details will turn out, and just for your personal satisfaction, I will do these details for you in this case. 8x minus x, of course, is 7x. Integrate that from 0 to 1, you get 7 over 2. 8 over x squared minus x, I can write that as 8 times x to the negative second. Integrate, lower bound, upper bound, 1, 2, respectively. Throw in, subtract, and common denominators, and that should have been a negative 8 right there. There we go. And there we have it. That's how the cookie crumbled. 7 over 2 plus 5 over 2, 12 over 2, or 6. So, key takeaways. This formula that we've been working with, it gives us the actual standard geometric area. We don't have to worry about negative areas or positive areas in the Riemann area sense. This is our familiar sense.